Yay!
Yay! All right, let's start talking about moment of inertia by treating maybe the simplest case, and that's going to be just a single point mass in circular motion around some central point. The problem is a lot of students have trouble with moment of inertia because it's sort of abstract. I mean, it's sort of like mass, but it looks more complicated than mass, and then it changes for an object depending on what the axis of rotation is. And so it's sort of a weird abstract quantity, but maybe we can help it make a little bit more sense. Let's start with a really, really simple case. So I have a little particle, mass m, and it's spinning around the center. It's in circular motion, so it's instantaneous. Instantaneous velocity is here, right? V. So what we're going to do is try to find a better way to describe the rotational motion. And that's going to be with something called the angular velocity, the angular speed. You've sort of maybe seen this before, and it's something that we'll call lowercase Greek omega. Omega is going to be our angular speed. First, we got to figure out what units it should be in. Now, one way to think about it, it's sort of how fast it goes around the circle. So you might expect it to be maybe some sort of like degrees per second, but it's a lot more convenient to work. I mean, degrees are a little bit arbitrary, right? There's 360 in a circle, but there's a more fundamental unit of angle called the radian, which you're probably already familiar with. So here's where that comes from. Let's make sure we're all on the same footing. As we go around the circle, as m goes around the circle, notice that s, the amount of arc length, the distance, right, that the mass goes around the circle, is proportional to the angle theta, right? If m goes maybe up to here, theta is half as big. If it goes up a little bit farther, now theta is twice as big. So the amount of distance around the circle that the mass goes is proportional to the angle, right? So we're going to use that. In fact, what we know is if m goes all the way around, then how far have you gone all the way around? Then s is just equal to 2 pi times r, right? That's just the circumference of the circle. Okay, but go back and look at this for a second. So we're going to use that. But also notice that there is some magic angle here, just by process of elimination, right? Or whatever the property in mathematics is in analysis. There's some angle so that the arc length is equal to the radius. I mean, that's just going to be true. Like if I'm down here somewhere, for sure the arc length is a lot less than the radius, right? And if you go all the way over to here, then the arc length is for sure greater than the radius. It's almost 2r. So there's going to be some angle in here for which there is some angle so that s is equal to r. That's just going to be true. We're going to define that. It's some fundamental quantity, right? That's sort of a special angle where the arc length cut off by the angle is just equal to r. This is 1 radian. Okay, that's what we're going to define as 1 radian. Okay, where s equals r. Okay, well, we can figure out what that angle is, because if 360 degrees, let's write it in terms of degrees, because you're more familiar maybe with that. If 360 degrees equals 2 pi radians, right? 2 pi r, but now s is equal to r. So if 360 degrees is 2 pi radians, then that implies that 1 radian, I'll just divide it, is 360 degrees over 2 pi. So that's 180 degrees over pi. And if you do that, what you get is something like 57.3 degrees, almost 60 degrees. That's the special angle. So that angle means that the arc length s is equal to the radius r. Cool. All right, so that's 1 radian. Okay, so in general, we said that the arc length was proportional to the angle, and the proportionality to the angle is just r. So S, the amount of arc length, is just r times theta, theta in radians, measured that way. So what happens if that's the distance S compared to r and theta? I mean, if this is the distance that the mass goes around the circle, what did we do before a long time ago? If you want to find the speed of the mass, not the velocity, but the speed of the mass around the circle, that's just ds dt, right? So the speed is just ds dt, and that's just going to be equal to, okay, now we have to be a little careful, right? Because it's two things multiplied together on the right-hand side. There's r and there's theta. So if I'm going to take the derivative of the right-hand side, you might think, uh-oh, I've got like a product rule, right? It's theta times dr dt plus r times d theta dt. But r is constant. Why? Because we're moving in a circle, right? R doesn't change. That's what being a circle means, is that the radius is constant. So R is just a constant. So this is just going to be R d theta dt. So that means that V is just R times this new thing, d theta dt. That's the number of radians per second that you're spinning around, right? And that's what we're going to call omega. All right, boom, there we go. So omega is in radians per second. That's the unit for omega. And that's how you tie the two together. So that's how you can figure out if a solid object is spinning around at so many radians per second. A point on the solid object has a linear speed v. You just multiply by r. How far is it away from the center? And that kind of makes sense. That means, I mean, a solid object is going to rotate. Like if this thing were rotating, all of these points are all rotating with the same omega, right? But that's what a solid object means, is that they all go 2 pi radians. They all go the same amount, one complete circle per second. No matter where you are in the circle, that's going to be true. But like on a merry-go-round, how fast you're going depends on how far you are away from the center. For sure, if you're right near the center, you're not going to be going as fast, because this little circle, if you're right in here, that little circle, you complete that little circle in the same amount of time as you complete the big circle here on the outside, but you go farther in the big circle, right? So it makes sense that you're going faster the further out you're going. So to compute your linear speed, you just multiply by r. You just calculate the angular speed, multiply by how far you are away from the center, and that's your linear speed v. All right, very cool. So we still haven't talked about moment of inertia yet. Here's where it comes from. Here's sort of the motivation. So what is the kinetic energy of this thing as it goes around? We know that that's 1/2 mv squared. But now we can write that in terms of the angular speed. So that's 1/2 m r squared omega squared. And here's what we like to do. This is the rotational kinetic energy, right? And what we like to do is write it in terms of the rotational speed of this thing. So there's our factor of, here's our factor of 1/2. We like to make it look like the ordinary 1/2 mv squared you've seen before. So for something that's going from place to place, we said that that's 1/2 times its mass times a linear speed squared, right? So what we're going to do is do almost the same thing. Here we've got 1/2, and we're going to call this a new thing. We call it the moment of inertia and give it a funny letter I. But really, this is sort of the rotational mass. That's another way of thinking about it. And then it would be times, the kinetic energy is 1/2 rotational mass times the rotational speed squared, right? So it's the same sort of idea, just written in terms of different letters. The rotational mass, the concept kind of makes sense. I mean, what is ordinary mass? Ordinary mass, we said, mass is, I mean, back to Newton's second law, it's just F over A. It's the resistance to being accelerated. Right? If you push on a ping pong ball, it accelerates quick because its mass is low, right? It doesn't have very much resistance to being accelerated. If you push a refrigerator, it accelerates very slowly because it's got a lot of mass, right? A lot of, in other words, inertia. It's got a lot of resistance to being accelerated. So that's where the inertia part comes from. Rotational mass is just going to be how resistant is this thing to being spun, to having changes in its spin rate. So that's why we call it a rotational mass. So for a point particle, I'll be a little more clear. For a point particle around a distant center, the reason I'm trying to be careful is because I'm not saying that the mass is rotating about its own center. This is just a point mass rotating about some other center, is what I'm trying to say. So the moment of inertia, its rotational mass is just mr squared. And we use that to calculate kinetic energies, rotational kinetic energies. Because, oh, I didn't even write that down. Because rotational kinetic energies is just 1/2 I omega squared. And the nice thing is that's going to be true for every rotating object. All we're going to have to do is figure out what the rotational mass is for different objects and plug that in. But the relationship to calculate the rotational kinetic energy always stays the same.